morning class. Today we're going to talk about modular arithmetic and use that as a stepping stone to the RSA encryption scheme. So let's start back with something that you may be very familiar with, which is our division algorithm. Any integer is able to be expressed as the product of its divisor and the quotient added to a remainder, where the remainder is less than the divisor. As you'll notice, if we divide these various numbers by 7, we have the remainders. With modular arithmetic, we're concerned with the remainders. 1, we have a remainder of 1. When we divide 2 by 7, we have a remainder of 2, and so on. When we get down to 7, 7 goes into 7 one time, but we have a remainder of 0, and it's going to continue like that. You'll notice that our answers are limited to the numbers 1 through 6. When we go beyond 7, then we start again with our remainders of 1, and so forth. And you notice that 23 and 2 each have the same remainder when divided by 7. Modular arithmetic is a way of classifying all the integers into finite sets. For instance, all the numbers that have a remainder of 2, or all the numbers that have a remainder of 1 when divided by 7. Those would be the integers mod 7. I would say that. But this is not a new concept to you. For instance, the days of the week, all the days since the beginning of the earth would be could be classified according to the remainder when divided by 7. For instance, a day with a remainder of 1, you might call it Sunday. And another example that you're familiar with would be even odd numbers. Think about the integers mod 2 and some various examples we might use. For instance, 37, 44, 62. We take 37 divided by 2, our remainder is 1. 44 divided by 2 gives us a remainder of 0. And forgot my numbers, but 62 divided by 2 also gives a remainder of 2. If I were to keep on going and giving more examples, it would become obvious that this set of numbers are the odd numbers, this set of numbers are the even numbers. So another name for the odds would be the numbers with a remainder of 1 when divided by 2. Or all odd numbers would fit into the class of numbers that are 1 congruent to 1 mod 2. Likewise with the even numbers. And then a more classical example when introducing the topic of modular arithmetic would be the clock. Wait a minute, Vernon. They might not understand this. So
let's go to a real clock.
With a clock you may be more familiar with, going in the clockwise fashion even. We're at a little after, a quarter after 2, and if I was to meet someone in 5 hours, then it'll be a little after a quarter after 7. But what if I want to meet someone in 25 hours? I'm not going to plan it out that way. I'm more likely to use modular arithmetic and start my counting over every time I get to 12. Or I might keep track of AM and PM. Well, the point is, I would be able to calculate that it's actually a little after a quarter after 3, the next day when I'm meeting the person. As an example of modular arithmetic where 12 is our modulus. The number that we divide by is referred to as a modulus. So you can think of clock arithmetic as the explanation for arithmetic mod 12. So we looked at arithmetic mod 7, arithmetic mod 2, and arithmetic mod 12, and how that works. So let's take this and apply it to the context of encryption. If we have a message we want to send, and we have a list of characters we want to use to communicate that message. If we were to use the English alphabet, we might limit ourselves to 26 letters, and any additional punctuation we feel necessary, or likewise a space would be helpful. So you probably just want them. So if you want efficiency, then you would use the minimum number of characters possible to still communicate clearly. Or if you just want to make it more confusing, then you might just maximize your number of characters that you're choosing from. Alright, so the idea is to be able to use our modular arithmetic to encrypt something, we need to arrange it in a way that's easy for our computer to manipulate mathematically, arithmetically, if you will. So let's do a substitution. Again, here's another opportunity to further encrypt would be to arrange these in a non-straightforward approach. But for the sake of instruction, let's use the most intuitive approach for our immediate audience. 8 to 1, 0 to 26. So now that we have a message, now that we have a substitution to numbers, let's think of a message we might want to send, and we'll start with something small. The message that we want to send is referred to as the plain text, and in this case we choose the word prime. So we have 5 letters, and we notice that our largest number of digits is 2. So even when we have a single digit number that's represented with 2 digits, so that in the decryption process we know to break everything back into 2-digit spaces. There's no confusion about where the division of the symbols occurs. And let's use our substitution map on the plain text. So we have 16, 18, 9, 13, and 5. And we would bunch those all together. I drew them with spaces, but we wouldn't want to use our space character when sending it, because we don't intend to communicate spaces in between them. But there's the mapping, and then we want to choose the size of the blocks that we're going to use to send it in, because depending on the size of the message, it may not be computationally practical to operate on the number that's obtained by concatenating all these letters, but we're more likely going to break it into chunks or blocks.